All right, this looks like a harder problem than other, Stokes theorem problems, or excuse me, other flux problems that we've seen in the past. Because not only do we have to compute the flux, but we're not even told the vector field. We're told that we have to compute the vector field. The vector field is the curl of this other thing, and that's extra effort that it would seem like we would have to put into this just to figure out what we're computing the flux of. So we can take a different point of view on this, though. View this instead of saying that we're computing a flux of a vector field f. Sure, we're computing the flux of f, but by the way, here's the anti-curl of f. See what I'm saying? This is the vector field whose curl is f. So from that point of view, and let's give this a name. By the way, like we could call it I don't know. I don't want to call it G, but let me call it H. I don't. Anyway, here we go. So let's say H is this thing here. It's y squared z minus z squared e to the y, comma, etc. Okay? So F is curl H, and I want to compute flux through, we've got some surface of F dot ds. Oh, well, hey, wait a minute. This flux, this vector field is a curl of something. And, of course, flux of a curl, by Stokes' theorem, is the line integral around the boundary of that thing itself. So this is where we use Stokes' theorem right here. Does that make sense? Yeah. I mean, think of this as, if this were here's an analogous problem. Compute the line integral around, over some curve of the gradient of some function of f dx. And you could say, oh my gosh, well, they didn't even tell me the vector field. They gave me some function. What am I supposed to do with that? And now I've got to compute the gradient of it, which is effort, and then I've got to do the line integral. Or you could say, no, if they're giving me that function, they're telling me what the anti-gradient of my vector field is, and then I'll just use the fundamental theorem of line integrals. And reduce a one-dimensional evaluation down to a zero-dimensional evaluation by using the fact that I was given an anti-gradient. Here, same thing. I'm reducing a two-dimensional evaluation, namely a flux, down into a one-dimensional evaluation because the way this field was given, I was told what the anti-curl was. You see what I'm saying? It's really very analogous to one of these. I love these analogies. Different dimension contexts, but otherwise very similar, perspectives on problems. And I claim this problem is not unlike a problem like this. So the fact that your vector field was given as a gradient of something allows you to use the corresponding boundary theorem, and that's what's going on here. So anyway, let's wrap this up now. So here we have. We're going to do an integral around the boundary curve, and H is this, it's this thing here, right? So, okay, now it is looking a little bit ugly. Let's go ahead and write this down. Hope we get lucky here. Let's see, y squared z minus z squared e to the y. Let's see, x e to the z. And let's see, xy plus xz squared. Yikes. Okay, now let's see, dot dx. All right, well, let's write that differently. Dot x prime dt. So if we parameterize our boundary, our little boundary curve, then, okay. So let's pause for the moment. This doesn't seem to simplify anymore right now. Let's pause and take a look at our curve, this boundary curve, and see what we can deduce about this guy. Okay. All righty, well, our surface was this. Our surface was, we're looking at part of this paraboloid where x is greater than or equal to 0, and x was a paraboloid. So what we've got is a paraboloid kind of thing, sort of like that. And the boundary curve, though, is like that. The boundary curve is this curve in the YZ plane. Does that make sense?
Yeah.
Everybody cool with that? So that's in the YZ plane. Okay, so two things I know. One is I can parameterize that circle without too much trouble. But more importantly, most immediately what I can tell is that x is always 0 on that entire curve. Everywhere on that entire, I mean, I can write down the parameterization, sure, right? But x is going to just be 0. So going back up to this expression, 0, 0, 0, all this stuff is just going to be flat 0. Right? And that's kind of cool. And let's write down the rest of the parameterization just to be complete, but that's the neatest part. So I'm going to have that be cosine t and sine t. Right, then I can write down x prime, y prime, z prime. And let's see, well, that is 0. This is negative sine t. This is cosine t. So what else do I know? Well, this x prime here, let me just write down, oh, I kind of, okay, that's x prime. Let me rewrite, give myself some space. Okay, I've got line integral. X prime is 0, and then this is, stuff. But I already agreed that in here, x was 0, so both of these are going to be 0, and then that's a bunch of stuff. So I got some formulas in here. Whatever, I'm multiplying it by 0. Who cares if it's formulas? Right? Yeah?
X is 0 even though in the problem it says x is greater than or equal to.
Yeah, because that's the surface. The surface is, you're right, it's this kind of paraboloid. I didn't draw that very well, but the surface is the paraboloid. The boundary of the surface, though, is, if you just look at the geometry of it, right? It's, yeah, exactly. Does that make sense?
Yeah.
Okay, yeah.
Seems like the same thing as the anti-kernel. Could you use that same thing we just learned in class today was surface independence? Could you use that?
Yeah, absolutely. Now, we hadn't done that at this point. You're right. So since we've only done Stokes theorem, we hadn't gotten to surface independence. But yeah, that would be a great way. Another alternative way to work this problem would be to say that, well, you could just evaluate, forget about Stokes' curl theorem, and just say, well, I could just compute this vector field, this vector field f directly, use surface independence, and say, I don't like that paraboloid. I like that flat disk there. And just compute it directly. And your normal vector would be really easy. It'd be 1, 0, 0. And then hope that the curl works out nicely. And off the top of my head, I don't remember how that works out. But if it does work out nicely, it's not immediately obvious whether it is or not. But that would certainly be a perfectly reasonable thing to try. Absolutely. Yeah. So let me just wrap this up, though. I mean, is everybody happy with how I claim this works out? I claim that these components are 0 because x is 0 on my curve, and that's 0 because it's x prime, which is 0. So this whole thing is just 0. Everybody good? Okay. All right.